Welcome, everyone. It's great to have you here for the inaugural seminar in the New Directions in Cooperative AI seminar series. And it's great to have Vincent Conitzer here with us today. Before beginning, I wanted to tell you a little bit about Cooperative AI, the foundation in the seminar series. So on the right hand, you can see the trustees, myself, Eric Horvitz, Gillian Hadfield, Rui Donnelly, Dario Amode, and then in the center bottom is Lewis Hammond, who's been a really critical contributor to standing up the foundation. Our mission, or rather the Cooperative AI Foundation, which we pronounce as SAFE for the acronym, is a charitable entity whose mission is to support research that will improve the cooperative intelligence of advanced AI systems for the benefit of all humanity. And I'll unpack that in a moment. This is backed by a very generous philanthropic commitment from the Center on Emerging Risk Research of $15 million. And really to communicate to the community, our goal is to spend this effectively and really, the intention is to try and make this foundation as energetic and engaged as possible. And we can imagine scaling it up even further. If you're interested in learning more about the foundation and this broad effort, you can go to cooperativeai.com or .org or .foundation, which will all take you to the same place, and you'll find some references, suggestions for that are also very welcome. So I want to tell you a little bit about the mission to unpack how we're thinking about it. First, this sort of first green bolded part of supporting research refers to standard academic grant making, but also fostering research in other ways, such as organizing workshops and other events, supporting students, awarding prizes, and providing educational tools. The next highlighted term, this key verb, improve, indicates that we're really thinking about counterfactual impact. So we're asking the question, if SAFE were to support some initiative, do we see it counterfactually really making a difference for the latter part of this proposition? And a second part is that we're thinking on a time horizon of 10 to 20 years. So we're not asking, will this be good for the research in 1 year or 2 years, but will it really make a difference for this final part of the proposition, the benefit of all humanity, on a 10 to 20 year time frame? Okay, the next part of the mission statement, cooperative intelligence, is a bit of a new and underdefined concept, which in our understanding so far, it refers to the skills required for promoting cooperation between humans, machines, and/or organizations, and every possible sort of dyad in community you can imagine combination there. The bet implicit to that is that cooperative intelligence is broadly beneficial. And so by improving that, will help humanity with its global cooperation challenges, also humanity in our day-to-day cooperation challenges. Advanced AI systems, again, point to the systems of today, but especially those that could come in 10 to 20 years, which we imagine being far more capable than the systems of today. So we're very excited about bets or proposals for the Cooperative AI Foundation that complement advances in machine learning and artificial intelligence. And then finally, the target goal is the benefit of all humanity is also something worth reflecting on because it is a nuanced notion, and many people have different ideas of what that means. But the key thing we want to emphasize is that we don't take for granted that research or cooperative intelligence is inherently beneficial. We think that's a part of the Cooperative AI Foundation's mission, is to explore when certain interventions will be most beneficial and when maybe they're only slightly beneficial and when maybe even they're harmful. Great. So now to tell you about the New Directions in Cooperative AI seminar series, we will be having the seminar series fairly regularly. We're looking towards bringing leaders in the field, but also new thinkers who have promising visions for agenda setting contributions or frameworks or proposals that the Cooperative AI Foundation could support. Specifically, we're also interested in you submitting proposals for future talks in the series. You can find out online how to do that. We will give sort of notification within 1 month of rejection, sort of an R&R or acceptance, and we'll work a little bit with proposals to help tailor them to the seminar series. And then finally, successful proposals will receive a $5,000 honorarium in recognition of the work that will need to take place for the presentation because we're not looking for normal academic talks. We're really looking for these visions for how the field or multiple fields and disciplines could be steered according to the mission as just discussed. So this is something that academics don't regularly do. We sometimes do, perhaps as principal investigators, we do that for our labs. Sometimes we do it for our fields. And here we're asking, let's even do it for multiple disciplines. Are there visions for how AI research and sociology can come together and produce a sort of productive research stream that will help achieve the mission, or other examples like that? So with that, I'm really excited to introduce this first seminar series. We have Vince Conitzer, who has a number of affiliations with Duke University, University of Oxford, and then recently he's going to be moving soon to Carnegie Mellon University, where he will be starting a new lab known as Focal, or the Foundations of Cooperative AI Lab. And the lab's goal is to create foundations of game theory appropriate for advanced autonomous AI agents with a focus on achieving cooperation. We also have Edith Elkind with us, who will be discussant. She is the professor of computing science at the University of Oxford and has expertise in algorithmic game theory and computational social choice. And finally, we have Joe Halpern joining us as another discussant, professor of computer science at Cornell University, who has expertise in game theory, decision theory, computer science, reasoning about knowledge and uncertainty, and causality. So with that, I'll turn it over to you, Vince.
All right, thank you, Alan. And everybody should now be able to see my slides. Great, so thank you so much. It's such an honor, and I'm so excited to give this first talk in this amazing seminar series. I'm also very thankful for the support that Focal, the lab that Alan just described, is getting from SAFE, and also the Center on Emerging Risk Research that he mentioned. So we're very excited to get started. So the topic of today is, often when we think about AI agents cooperating, we're inspired by how humans cooperate, right? In many ways, we're, as humans, very good at cooperation, but this also leads to these somewhat anthropomorphic approaches to it, right? I think this is true for AI somewhat more generally, that we're often inspired by how we as human beings do things. And that's a natural way to proceed, but it also has its limitations. You can see here on the right of the slide a story about two self-driving cars where the one, they're communicating with each other, and the one is somewhat threatening to the front one, trying to get past. So you can read that story for yourself. And it's intended to be a little bit funny. I don't know if it's really all that funny, but to the extent that it's funny, the reason it's funny is that I think at some deeper level, we don't really expect self-driving cars to behave this way, right? When they really get fully deployed. And I think that should tell us something. So the thesis for today is that AI agents may actually cooperate better if they don't resemble us. So let's explore the ways in which they could be different from us in ways that could help us avoid game theoretic dilemmas. That's the thesis. Well, I'll provide some evidence for it, but it's not going to be the kind of thesis that I prove in this talk. As Alan said, this is really more an agenda setting talk. I want us to be able to think about these kind of questions, and we're going to be doing that in Focal. And again, that doesn't mean that I want to dismiss approaches that focus more on getting AIs to behave as humans. I'm very interested in those still as well. But that's the basic idea of this talk. So here is an outline for the talk. I'm first going to talk about what I'll call tragedies of algorithmic interaction. And the word tragedy here is used in the sense of, you might be familiar with the tragedy of the comets. And there's going to be a little bit of a game theoretic flavor to this talk. So we're going to have some examples, some worries. Then we're going to step back and think about the design of intelligent agents. And in particular, a point that I want to make is that even if we solve the value alignment problem, and even if we have highly intelligent systems, we may still get these kind of tragedies where, due to the interaction of the systems, we get really bad outcomes. Then I'll take some time to talk about whether AI systems should cooperate like humans do. What are the benefits of that? What are the shortcomings? And then I'll talk about techniques for achieving cooperation in game theoretic settings that should work kind of regardless of whether we're talking about humans or about AI agents or really any other kind of entity. And then I'll talk more about techniques for achieving cooperation that really don't seem to make sense in human contexts, but that really might make sense in AI contexts. I'll close with some open questions and a call to action to study these questions more. So here is an interesting story you may have seen before. This is really more a comedy than a tragedy. There was this book called The Making of a Fly about genetics that I'm sure is a wonderful book. But somehow, at some point, somebody noticed that, well, on Amazon, this book was selling for a really, out there amount of money, right? I mean, here it's about $2 million for the book, which again, I'm sure it's a great book, but there seems to be no reason that it should be selling for $2 million. And somebody figured this out and was wondering what was going on. And eventually that was figured out. So what was going on here was that these prices were being set by algorithms. And these algorithms kept updating the prices in response to each other. And so eventually, actually, the price went up much further. So it was almost $24 million here. And what exactly was going on? Well, there are two sellers that were setting their prices algorithmically. And one of the algorithms was undercutting the competitor, right? So you can see down here in this box, right? So the one seller was ProfNath. And there, ProfNath always set its price to be slightly below the competitor, right, to be the lower price. Interestingly, the other one decided actually to set a somewhat higher price than the competitor. I'm not sure why that was. Maybe they wanted to appear to be a higher quality seller, or maybe they actually wanted to buy the book from the other seller to then sell it with a markup, right? But you can see from these ratios that if this happens over and over again, the price is just going to go up exponentially. And eventually this was figured out and then it stopped. So it's kind of an amusing anecdote. Nobody was harmed here. I don't think anybody went and bought this book for $24 million. But you can see kind of things going wrong because of the interaction of these two algorithms that in and of themselves might seem sensible enough. Here is a somewhat more serious story. This is the flash crash that you may be familiar with. In 2010, this is what you see here is the Dow Jones Industrial Average. Suddenly it took an enormous dip. And I think even today, it's not totally clear exactly what all happened there, but it is clear that high frequency traders, right, so those are algorithms, had a big role in this. Right? And there seemed to be some phenomenon happening that they were selling back and forth to each other in a kind of hot potato effect that really drove down the price. And eventually things recovered, but this certainly spooked a lot of people. And so here we see some examples of algorithms interacting badly. And my worry is that, well, we haven't seen the last of this, right? As algorithms and AI take over more and more of our world and make more and more decisions in our world, they'll also interact more with each other. And I think the stakes will only get higher. So I'm afraid we haven't seen the last of this type of phenomenon. Now, on the other hand, you might be a little bit optimistic and think, well, in some sense, maybe with these examples, the issue is more artificial stupidity, right? These algorithms just aren't very intelligent. They're maybe following somewhat simple rules, and that's what's causing the issue. And so you might hope that as these systems become more intelligent, we wouldn't see this kind of thing happening. Now, I do think we'll see these systems become more intelligent, but I'm going to argue that that doesn't mean that we should expect to not see these kind of things happening. But let's take a step back and let's rethink the design of intelligent agents, such as the ones that might control these systems. And so we might go to Russell and Norvik. So here is an image from, this is actually a somewhat older edition of the textbook. And what I'll show on this slide represents a somewhat older view that I think was very common in the AI community some number of years ago, and certainly isn't Stuart's view exactly anymore. But so here's the idea, right? So this is often how we think about the design of an agent, that we have this very modular entity that senses the environment, gets to act in the environment, and has a model of what the world is like, how it will change in response to actions, and also as utility. So some kind of measure of how much it values each state, and that's what it makes decisions based on. But again, this very modular entity that, again, I think at some level is kind of anthropomorphic. And then also in text, in this older edition, it says, well, where does this utility come from? And it says, well, some authority is going to impose an objective performance measure, right? some standard is going to be established, and that's all the agent needs to worry about, just follow that objective. And that, I think, by now we have very broadly realized that it's not that simple, right, to actually figure out what that objective should be. And so that's kicked off a lot of research in value alignment, AI value alignment, that especially if you interpret it broadly, there is a lot of work being done on that in various different contexts. I think it's a really important problem. I've worked on it myself, and I think probably it's still understudied, but I'm glad at least it's getting more attention than it used to. But for the purpose of this talk, I want to point out that even if you have solved the AI alignment problem just about as well as you might expect, you might still get these kind of tragedies. So here is an example of that. So imagine that we have two agents, each of them providing part of a service. Each of them chooses a quality, QI, where I is the agent, with which they execute their parts. Okay. And so the overall quality, we'll assume, is determined by the lower of the two numbers, right? Whichever agent kind of puts the least effort in, that's what's going to be the quality of the service overall. And that is actually what both agents care about the most. They mostly care about overall quality, which is presumably also maybe what we, if we're still involved as human beings, what we care about. So actually, everybody is pretty well aligned, except there's a slight difference that the agents, while they care primarily about overall quality, they also have a slight incentive to be the lower one, right? The one with the lower quality. You might imagine an environment where the lower agent, right, the one that's producing lower quality, actually gets a little bit of extra attention, some extra resources. That seems intuitively sensible, right? We want to get the minimum up, so we focus on the agent that's currently producing the minimum, the lower quality. But if they actually don't have an incentive to get those resources, something funny happens. So here is the game that results, right? So imagine that they choose some multiple of 10 as their quality up to 100. So here is the game. So let's take a look. So what do I want you to take away from this big game? Everybody is much happier here near the top left, right? Where qualities are high. And that's, again, what both agents care about the most. But they don't always value things exactly the same, right? Because if you're the lower one, you get a little bit higher utility. Nobody really wants to be here at the bottom right, where utilities are generally low. And yet, turns out the only equilibrium of this game is the bottom right entry. Okay, that's the only equilibrium of the game. That also means that your typical learning algorithms, if the agents are independently trying to learn how to maximize their own utility, they will eventually end up here. So that is a concern, right? Even though all the numbers are pretty close to each other, within any entry, both numbers are always pretty close to each other, right? And by scaling this thing up further, you could make them even closer to each other. This game, incidentally, is known under a different story as the Traveler's Dilemma. Okay, so that's our motivation. Don't know if you've seen the Traveler's Dilemma before, but at some level, it's just a souped up prisoner's dilemma, which I'm assuming most people here have seen before. But just to remind everybody, this is the prisoner's dilemma. We have a red agent, the row agent, the blue agent is the column agent. Each of them chooses to cooperate or to defect. Both agents would be better off if they both cooperated, or they would be pretty well off. They would get 2. But unfortunately, each agent has an individual incentive, it appears, to defect, right? Because no matter what the other agent does, you're better off defecting than cooperating, right? The row agent here would get 3 instead of 2 if the blue agent cooperated, and 1 instead of 0 if the blue agent defected. Same thing for the blue agent. And so under a standard game theoretic analysis, we would end up here, 1-1. Okay, so that's a tragedy. Okay, so let's talk about humans briefly. So much is made of human ability to cooperate, and there's definitely something to that, right? So you can find all kinds of articles online that celebrate humanity's ability to cooperate. Of course, it doesn't always work out that way. You can also find plenty of articles that laments how we failed to cooperate when really we should have. So, maybe at some level the jury is out. So here I want to take a slide again, with the kind of this particular seminar series in mind, to have for later on to propose some direction for discussion. So should we make AI more human-like? Will that help us with cooperation? And now, what does it mean to make AI more human-like in this context? You could think about giving agents some kind of pro-social inclinations, like altruism. You could think about ethics, right? And we could try to code that into our agents. That's a direction I really value, and I think a lot of good work gets done there. But sometimes also I see papers that leave me wondering a little bit that, for example, the paper might show that, look, here's this tragedy that would happen with the ordinary utility functions. And if we just change the utility functions to this other utility function, look, everything becomes much better. And sometimes it leaves me wondering, like, well, great, but have you just assumed the weighted problem, right? Can we really, yes, just the fact that you in your experiment can change the utility function doesn't necessarily mean that this is how it would play out in reality. Another related idea is that there might be norms and rules. And that I think we can definitely encode to some extent. I'll get back to that in a more traditional game theoretic view. Another question is whether we as human beings have certain cognitive limitations. And I would argue that those sometimes limit the tragedies that we see. For example, in the traveler's dilemma, if you really get people that play the traveler's dilemma, they won't play that horrible outcome. And part of that might be that, to realize that that's the only equilibrium, you really have to go through a lot of levels of reasoning. More broadly, I think just in ordinary life, the reason that people often cooperate and follow the rules and follow the norms is also that we just don't spend all our time thinking about all the ways in which we could deviate and take some advantage for ourselves, right? We just don't even probably see all the ways in which we could take advantage of the situation, and maybe we don't even want to. So this quote here, I think, captures something of that. But then there's a question of like, well, should we then try to limit our AI agents, and is that even going to be possible? Good. Anyway, for this talk, I'm going to again focus on, well, maybe there are ways to get AI to do better on cooperation than humans. But maybe that would somehow kind of happen naturally. But here I'll talk a little bit more about deliberate design decisions on our agents that would help with that. Okay, so just for illustration, I'm going to quickly go over some techniques for cooperation in a game theoretic setting that I think work regardless of whether you're talking about humans or AI agents. So more traditional game theory view. So a common, maybe the most common way for game theorists to see this is, well, one reason that people cooperate is that games don't occur in isolation. Usually you play with somebody many times. And yes, you can take some advantage now by defecting, but you'll ruin your relationship and the other person is going to defect on you in the future as a result, making it not worth it. You can formalize this as the grim trigger strategy. And this leads to the Folk theorem in game theory that says that if agents are sufficiently patient and this game goes on forever, then you can always sustain cooperation in this game, in any game. It's a really powerful result in some way. Also, actually, it turns out to be quite easy to compute such equilibria. So lots of advantages. But also, I think there are still limitations, right? There's this question about being patient enough and having the play repeated over time. So here is kind of a cautionary tale. So in joint work with Catherine Moon, we investigated this issue that, well, the common assumption here is that defection is immediately observed. In reality, maybe often it's observed through a social network. I defect on A, then A tells B about that, then B tells C about that, and then later on, C doesn't want to cooperate with me, right? But maybe it takes some time for that information to reach C, and if I discount the future, maybe I don't really care about what happens so many rounds from now. In this work, we found an algorithm for finding the maximal set of cooperating agents as a function of the network and how much they care about the future. And now we had this algorithm, so we could run some simulations, and we kind of expected that, oh yes, as you, for example, increase patience, more and more agents will be willing to cooperate. What we actually saw kind of surprised us, namely that does happen, but in a very extreme way. So it turns out that you get this phase transition that as a function of the parameters, how much do you benefit from cooperation and what is the discount factor? You either get everybody cooperating, everybody is able to sustain cooperation, but then if you move the parameters slightly further, you can get a complete collapse of cooperation where nobody is collaborating or nobody is cooperating anymore, right? So I think this is kind of a sobering tale that cooperation might be very brittle. You might be in the situation where everybody's cooperating and suddenly it falls apart just because of a slight shift in the parameters. So there are limitations to that. Another one that I want to indicate very briefly here is we've been working on disarmament games. What is a disarmament game? Here's an example where we see a game. The story of this game is somewhat too convoluted, so I'm not going to present it. But this game turns out to have two equilibria, two Nash equilibria over here. And moreover, if you had a Stackelberg model where one player committed to the strategy before the other player, you would also still end up here. Okay, and this is not a great outcome because this one here would be much better. It turns out if you can get players to commit not to play certain strategies, you can do better in this game. For example, the following can happen. The column player could commit not to play the middle column. Okay, so they're not committing to what they are going to do. They're committing to one thing that they're not going to do. And the reason to do that would be that once you've removed the middle column, it creates an incentive for the row player, because at this point we would still reach this outcome. It creates an incentive for the row player to remove the top row. Okay, and once that top row is then removed, now this outcome, the one that we wanted, becomes the equilibrium. So this is one other way that you might get the cooperation. Unfortunately, one issue here is that, well, you notice I set up a kind of complicated game. This isn't always possible, right? You need to be kind of lucky that your game has the right structure to be able to do this, as it is here. Also, it's NPR to figure out whether this is even the case, whether you could do this. Turns out it would be better if you could commit to not play certain mixed strategies. Okay, but that seems like kind of a strange thing, right? Like at least in our usual human context, you might think, well, you might be able to commit to not play a certain strategy by, for example, destroying a resource that you have. It seems harder to commit to not play a certain mixed strategy. How would you do that? We'll come back to that. Okay, so now, cognizant of time, but I want to briefly talk about some techniques for achieving cooperation that wouldn't fit humans. Good. And here, again, the idea is that AI agents might be very different from us in various ways. And this really gets us to think again about the foundations of game and decision theory, right? For example, what should you do if you knew that others could read your code according to which you make decisions? It's not something that humans typically would face as an issue, right? Like maybe somebody is scanning your brain, but even then, it doesn't seem to be quite the case. What if you're facing somebody who is running the same code? That also seems like a strange scenario for human beings. Here I took Mark and Scott Kelly, our NASA astronauts, who are also identical twins. That's maybe as close as possible as you might get to two people in the world that are really the same in their decisions, but still maybe not that extreme. Also, there may be issues of imperfect recall. What if you kind of systematically forget things, right? It's not like I forget stuff all the time, but maybe it's not that systematic, right? But if you knew for sure that in certain situations you're going to forget what happened before, then what should you do? So it's maybe the situation in the movie 50 First Dates where Drew Barrymore's character has some condition by which she forgets everything that happened the day before every day she wakes up. But normally in human context, this doesn't happen. But for programs, for algorithms, this certainly could happen, right? They might realize that they'll be executed again in the future with a clean slate. All right, so here's a concrete idea. So going back to this idea of code being legible, this idea of program equilibrium. So now we imagine here's just a regular prisoner's dilemma, and we're not going to repeat it, but we have the two agents, and instead of just picking an action, now they pick a program. The agents pick a program, and now notice this particular program is an interesting one. So if they both pick this program, let's see what happens. So the program says, if the other uses the same code as I do, then I'm going to cooperate. Otherwise, I'm going to defect. Okay. if you think about this for a little bit, you'll see that this is actually an equilibrium, right? So, and it's one that will actually lead to both of them cooperating because they in fact do have the same code. So they will both cooperate. You could deviate and write a different program, but any different program you pick is going to get the other player to defect. And so it won't be worth it. There's quite a bit of research on this already. And much of this is about how do you make this more robust, right? You could imagine, for example, that, well, what if in a different environment, some people had converged on, or agents had converged on basically the same idea, but for some reason they wrote if my code equals others' code. And now they interact with the agents from the red environment, and they actually end up not cooperating because formally the code is not quite the same, right? This just doesn't seem quite robust enough. Critch has done work on actually analyzing the programs. Here I'll mention my student Caspar Oesterheld, who is starting the focal lab with me. His work on this, that's based on just simulating the other agent. So here is a way to do this that involves what I think, I think what we think of as instantaneous tit for tat. So what you're going to do is you're going to simulate the other program, figure out what it does against this program, and then do that. Okay, that's kind of the instantaneous tit for tat. You're going to do whatever the other player plays against this program. Now, of course, this might loop forever if they both do that. So because of that, we also add an exit clause that with some probability epsilon each run, we end up cooperating. Okay, so there's that idea. Based on this idea of program equilibrium, I'll just describe this slide at a high level. You can also think more generally about handing off your play in the game to an intelligent representative. And here we're thinking about doing that by specifying a utility function to that intelligent representative that then is going to play the game, but we don't necessarily know exactly how they're going to play the game. We just imagine they're a good game player, that somehow they have to deal with issues of equilibrium selection and so on. And so we don't know exactly, unlike in the previous slide, we don't know exactly what's going to happen, but we imagine that the agents are just generally good players. And so what we want to do now is agree on modified utility functions for the agents. And we want to modify those utility functions in such a way that no matter how they play, as long as they play game theoretically, they will actually, it will lead to a better outcome for everybody involved. I want to briefly revisit the disarmament idea as well. So I said before that committing to not play certain mixed strategies could be helpful as well. So what if you could commit to your first few lines of code? And so unlike in the program equilibrium setup, here the programs don't even need to read each other. Okay, the programs themselves won't read each other. You might worry about the circularity that induces. But you do get to see what the other programmer codes up, right? And so the idea is here, the red programmer first puts a first line that says, well, with probability 40%, we exit the program here with cooperation. And then the blue player is supposed to add the blue player's first line, which is the same. Once that's done, the red player goes ahead and adds another line just like that, and so on. And they keep doing this until eventually the probability of cooperation is basically 1. Okay, so that's a way that you, with this disarmament idea, could actually get cooperation in the prisoner's dilemma. You can't do that by just throwing pure strategies away, right? Because somebody would have to throw away a defect, and at that point, the other player would have no incentive to throw away their defect strategy anymore. But this way, you could make it kind of gradual. And it turns out there's, again, a kind of folk theorem here that this actually, in some sense, always works. This way, you could always achieve cooperation in any game. Last idea I want to get out before we conclude, and I'll list some more directions for discussion. And that's this idea. So here we get a little bit more into philosophy, where we say, okay, suppose you're playing the prisoner's dilemma, not against some different agent, but you're playing it against somebody who is entirely like you. Right? Going back to Mark and Scott Kelly, imagine that you had a twin, maybe your identical twin, but more than that, it's your identical twin that always you agree with in any decision that you make. right? So you grew up together and you realize that every time somebody asks you a decision, like what flavor ice cream would you like, you always pick the same thing. You both say strawberry. And the next time you both say chocolate, right? Every single time. And then one day you're called upon to play prisoner's dilemma with your twin. Now we assume for some reason you're still selfish. You want to maximize your own utility and you don't care about your twin, but you know you're very similar. Would you then defect? And there seems to be a strong pull to the idea that, well, maybe you should cooperate, because if you cooperate, you can be pretty sure that your twin also cooperates. And if you defect, you can be pretty sure that your twin also defects. But this kind of goes counter to the typical reasoning in a prisoner's dilemma that says that no matter what the other player does, holding that fixed, you're better off defecting. Okay, so this gets more into philosophy and questions about evidential versus causal decision theory and so on. I won't go through the details here, but this is something we're very interested in as well. And you can ask the question of, well, what if you almost always agree? Really what we have in mind here, of course, is programs, right? If you're playing against a copy of yourself as code, then you could be pretty sure that that copy is going to play the same way. But maybe we have agents with overlapping code as well. All right. So again, very, very quickly, what I talked about, right? So so I argued that even with almost perfectly aligned agents, you can have these game theoretic tragedies. We talked about some ways of getting cooperation to happen that would make sense for humans and maybe as well as for artificial agents. But then also there are some ways to do it for advanced AI agents that don't really seem to make sense for human beings. And so I'll finish here. I just want to put this slide up here that has a number of open questions in this general approach, right? So under this general agenda, if we want to think about getting cooperation to happen with highly advanced AI and these kind of game theoretic settings, what are the foundations of the theory of that? And here on this slide, you can read many questions that fall under that agenda, and I'm sure there are others yet. So with that, I'd like to close so we have some time for discussion. So thank you very much.
Thank you so much, Vince. And if this was live, we would have a hearty round of applause by many people. Great, so we have 20 minutes, which is to say, and 140 people in the room. So I'm sure there's a lot of good thoughts in the room. Please do write them down and post them in chat. We'll try to get a few live contributions in the remaining time. But at this point, I'll turn it over to Edith and then Joe for some comments. So Edith.
Thanks so much. And thanks, Vince, for an exciting talk. Kind of a lot of food for thought. So what I was thinking about is obviously, so these are options that programs have kind of by virtue of being written down, right? So it doesn't really require sophisticated AI agents, right? So it might as well be implemented with humans and pieces of paper. But if we were to implement it on a large scale, and with really sophisticated AI agents, what sort of infrastructure would that take? Right. So for instance, if I am to commit to playing a mixed strategy in a large open environment, right? So how can it be checked that I'm tossing my coins the way I promised to toss my coins? So I'm thinking now blockchain smart contracts, right? And that makes it into a closed system that would be fairly difficult to enter. So do you think these approaches are compatible with having an open system that anyone can join?
Yeah, great question. And first of all, I should say that we're trying to think about these questions as much as possible in the abstract, in a way that they would hold for any infrastructure, for any architecture, and not get too specifically into the details of blockchain and so on. But your question is good, right? Well, so what is really required in order for these kind of techniques to be possible, right? As you pointed out, a number of them require code to be legible and verifiable. And so how would you establish that, right? And as you said, like blockchain or like some kind of smart contract idea might be one way to establish that. There may be other ways to do that as well, right? I don't know, in some sense that still seems potentially open, right? Well, but you're right that maybe there needs to be some infrastructure in place, right? If everything is kind of completely open in that there are no that there isn't some kind of base infrastructure to start from, I'm not sure exactly what would happen. Yeah, that's a good question. Mhm.
Okay, so I'm happy to leave it at that and over to Joe.
I will say, by the way, that this, I think, right, I mentioned earlier on this issue of like, well, are we just assuming the problem away by running simulations on agents that have some pro-social element added to their utility function? And you could ask that question with a lot of these directions, right? That maybe we're also kind of assuming the problem away by saying that, oh, if they can just read each other's code, then there are these nice equilibria and we're done, right? And maybe that's not quite right, because maybe we actually need to do something in order to make sure that that's actually what would happen in practice, right? To set up the right infrastructure. And I think that's a really good direction for thought as well, right? Like, what actions do we need to take in the world to make sure that these good solutions, if we think they're good, are in fact enabled? So I see your question in that line as well.
Yeah, and it seems like a good direction for this community also to pursue. So what would be the underpinnings for what we're trying to achieve? Okay, thanks, Vince.
So I had 3 comments, well, actually 1 big comment and 3 parts of it. You had focused, Vince, mainly on Nash equilibrium as the solution concept. And I want to sort of flag that and say, well, you know, if we're trying to think of foundations of game theory for agents who are programs, why is Nash equilibrium necessarily the right solution concept? So let me point out 3 issues. The first, and this is not just for programs, I think it's also true for humans, I think it would make sense to think of a solution concept that takes conditional cooperation seriously. I will do this if you do that. I think that's the way people behave. I think it might be closely related to notions of program equilibrium, where I can see your code and I can see that you're going to behave that way, but I think it would also make sense even without sort of this program equilibrium-like notion. So that's one issue, taking conditional cooperation into account. The second is taking computation into account. So I have a paper that shows that if you look at, in a precise sense, if you look at, try to develop a theory of computational agents and computational Nash equilibrium, it doesn't exist. And this would be particularly relevant for things like, you know, Edith mentioned the blockchain. So there, on the blockchain, we use cryptographic protocols, and those protocols typically assume that agents are polynomially bounded. And the kinds of equilibrium notions that make sense for polynomially bounded agents would be different. And in fact, our results show that things like arms races might arise when resource-bounded agents are best responding. And if you think about the Amazon example that you started with, it was sort of like an arms race. They kept raising the price because that's how, you know, they thought they were best responding. Our arms races are more sensible, arguably, but my point is that again, with resource-bounded agents, Nash equilibrium simply may not be appropriate. And finally, you had briefly mentioned imperfect recall. And I think that's actually a real issue when we get to both computational agents and human agents. People forget systematically. Agents actually choose to forget. I mean, we have programs that do things like garbage collection, where you throw out parts of your code. I mean, if you have limited space, you have to decide what you're going to forget, so that not only do you have imperfect recall, so when game theorists look at imperfect recall, it's just they draw these little pictures with extensive form games, and they draw little ellipses showing information sets. This is what you know, so that the imperfect recall is, so to speak, imposed exogenously on the game. But I would argue with computer agents, we actually might want to think of perfect recall endogenously. So you sort of have to decide what you're going to forget. And it turns out it's actually quite tricky to find appropriate solution concepts in the presence of imperfect recall. I mean, I know you're aware of this, papers of Piccione and Rubinstein that show problems with sequential equilibrium when you have imperfect recall. But here, I think the issue goes far deeper. So let me stop there. And I think the big point that I want to make is that I think part of, to me, the foundations of game theory for AI will involve thinking through solution concepts.
Thanks, Joe. Wonderful. Yeah, I couldn't agree more. And so, Nash Equilibrium is a good place to start, I think, because so many people are aware of it as a solution concept. I think, not all the problems are, the problems kind of they do go beyond Nash Equilibrium, right? In the sense that, like, prisoner's dilemma, there's a dominant strategy, a strictly dominant strategy. So at least some other solution concepts like correlated equilibrium won't really help avoid that.
Well, the computational issues do help. Raphael Pass and I have a paper where we showed, suppose you're playing repeated prisoner's dilemma for a long time and you forget how many rounds you played it for. That turns out to make a big difference.
Yeah, that makes sense, right? And again, this is very much in line with, I think, our thinking that in particular, as you said, like some of these things about mutual cooperation, that really lines up very well with program equilibrium. There are all these other ideas of mediated equilibrium, which is closely tied as well. And we're thinking a little bit about making those ties a little bit more precise. So generally, I agree. Also, again, this sort of evidential decision theory angle, right? That's what, if what I do is evidence for what you're likely to do, and maybe beyond that, beyond just saying that it's evidence, the actions we take might in some sense actually be logically related to each other. How do we think about those kind of questions? That I think also kind of goes beyond Nash equilibrium in ways that we're still figuring out exactly what's happening.
Yeah, we want to take maybe causal issues into account.
Exactly. Exactly. Yeah. So we do want to think about causality as well, and imperfect recall too, right? I agree with you that in artificial agents we can really structure the imperfect recall. That I think is very difficult to do on human beings, right? Like if you look at behavioral game theorists and the experiments that they run, it's very hard for them to do an imperfect recall game on somebody, right? It's like, okay, now you're supposed to forget this part. But artificial agents certainly could, for example, they could commit to forget something, right? And it's not hard to come up with a game where you would benefit from committing to forget something later on. So those, and also it might be somewhat inevitable, right? What I didn't talk much about, and by the way, there's a much longer version of this talk, or at least I have lots of other slides on all these kinds of issues with imperfect recall and so on. But one thing that we've been thinking about is also, well, this picture I showed earlier from Russell Norvik with the very modular agent, that is likely not really to be the case, I think, in real life, right? Even today, if you think about your personal assistant on your phone, let's say I had an iPhone, in which case I have Siri, but I don't really have like my separate copy of Siri running on my phone, right? In some ways, it makes more sense to think of all of Siri as one entity, but it's also not really quite one agent. So when you think about these kind of highly distributed agents, I think that naturally leads you into some form of imperfect recall as well, right? That a node in the system over here may have taken an action that this other node over here is not even yet aware of yet. And if you think of the system as a whole, then that kind of means the system over here forgot what it did over there. And of course, we might have other reasons to impose imperfect recall. For example, for privacy, right? We might want certain information not to be retained, which again would obviously lead you to imperfect recall.
Great discussion.
Let the audience take over.
Yeah, thanks, Joe and Vince. That was very interesting. So yeah, we have a few minutes left, 8 minutes. And the mechanism for getting a chance to speak is to raise your hand, which I see Blake found the button for that. So it's under reactions to raise your hand, and hopefully we'll get 1 or 2 comments in. Blake. Audio's not working. No.
I hear something, but it's very soft.
Yeah,
maybe
sorry.
take the question in the chat then, or?
Sure. Okay, why don't we go to Jillian, and while Blake's typing his question. Jillian.
Great, thanks Alan. Thanks, Vince, that was terrific. So much to think about here. I wanted to just focus in your traveler's dilemma example. You said even if the agents are fully aligned, we can still get these cooperative problems. And I'm wondering about your definition of alignment there, because if you think of, I think of alignment in terms of social welfare and not an individual agent. So that seems to me that's anyway, so I would just press on that. And then secondly, the way humans solve this problem is we have a norm that says, don't be so selfish that you drive the whole community down to this crappy outcome. We're going to kick you out of the game if you do that. Two thoughts.
Exactly. Great. Thanks for the question. That's a good question. I think, so first of all, well, I said almost perfectly aligned agents, right? So that they are a little bit different from each other, but they do all, so the sense in which they're almost perfectly aligned, and I mean, you could define this differently, right? But the sense in which they're almost perfectly aligned is that they value every outcome, every individual outcome of the game almost identically to each other, and also presumably to us as human beings who maybe care about the quality, the overall quality that's being generated here. I agree that in some sense, the system as a whole is not perfectly aligned, right? Because the system as a whole produces this outcome here that we all think is terrible. So I guess there are questions about the scope of what the thing is that we're considering to be aligned there. So yes, definitely. The other issue about the question about norms, I agree with that as well. And there, I think that ties more to this question of, where did I have this slide? I think I lost this slide. Oh yes, here, this one. Right, so I agree in some sense, norms would be a really good thing. And how should we think about norms? You could think of it in terms of an equilibrium of a larger game, right? Where we do have repeated play and interaction. As you said, like, if you're gonna defect, we're gonna kick you out of the system, right? Or if you choose a low quality, we're gonna kick you out of the system, or otherwise in some way in the future punish you. So that would be one way. And that way might succeed even on fairly, sociopathic agents that really are just in it for their own utility, but they realize that for the benefit of their own utility, they better cooperate. There are also these interesting ideas about, well, maybe we should inherently make the agents care about following the norms, right? And give them a sense of ethics, or give them a sense of altruism, or something along those lines. And obviously that, would be a good thing to have happen in many situations. Yeah, I just always wonder, and I haven't really figured this one out for myself yet. On the one hand, it seems like that's a good direction to pursue, that we want to build this into agents. But then also, are we not assuming away the problem? How do we make sure that we're not just assuming away the problem by running our own experiments that say, hey, our pro-social agents do really well. And then meanwhile, out in real life, agents emerge that don't follow those conventions and things go bad. And again, like as we discussed with Edith, right, that could in principle happen to many of these ideas here. So yeah, I haven't quite figured that out yet. How do we, or maybe we can say something about, well, as long as we control some reasonable fraction of the agents or some other measure of the agents that are out there, then that's enough. That's enough to enforce the norm. Yeah, I think there are many interesting questions to think about there.
So next up, I'll actually just read Blake's question. Blake, if I may, respecting the norm of precedence with hand raising. So Blake asks, what solution concepts or cooperation strategies may help when the agents in the game are a mix of human and machine? For example, things like reading each other's code. Maybe the human can read the machine's code, but the machine only gets to infer things about the human's commitments and patterns of behavior.
Yeah, great question. So, I outlined that some of the techniques here would kind of work regardless of whether the agents are human or AI or maybe something else. And so it seems like those should be robust. In other cases, so if it's a mixed population that are really playing a game directly together, some of these techniques may not work, right? Like the human cannot have their code read. Maybe there is a way in which you can still try to pull things into that direction, right? That maybe, we have a human player, but that human can delegate to a program after all. Then you might be able to get back to those ideas. But I think it's a good question, right? If you have this direct interaction between human and machine, or human and algorithm, which of these things will still work. And I'm inclined to believe that, yeah, some of them would go out of the window, especially in the kind of last part of the talk. But maybe there's a way to fix it. I'm not sure.
Great. I think this is going to be the last question, and I'm going to give it to Reshef Mayer, because I think that hand went up first, though I'm not sure how the interface works. So Reshef, over to you.
Hi, thanks. So I also typed it in the chat. So in your condition, like in this slide, you have this explicit condition that like your code has to be identical to my code. That's something that's easy to test, but it's a very strong requirement. I mean, we might be doing exactly the same thing, even running programs that are functionally the same, but they don't use the same code. So my question is, do you think we can also use some sort of program equilibrium that functionally tests if we're identical or similar, not by looking at the code itself? Maybe using a simulation or something like that.
That's a great question. And I think that is what some of these later works are trying to get at, right? I briefly mentioned, I didn't have a slide for it, but I briefly mentioned, Critch has been thinking about how do you get this to work based on analysis of the other program. Caspar has thought about, well, what if you simulate the other program, right? That's one way of getting at their functional behavior. Yeah, so to the extent that you can figure out what the function is that the algorithm computes, maybe that's enough, right? And so you can condition it on the function that is. That may be a difficult thing to figure out, obviously. And this is maybe where we get into questions about computability and so on. I do think there are interesting questions there of, so this is a little bit my fantasy, but you can imagine systems that have very complex programs behind them, right? So if you imagine a self-driving car, it might be hard for me to, if I'm another self-driving car, it might be hard to analyze that entire program or all the code behind the other car. But maybe the car could actually make it easier, right? So you could imagine that, look, I'm a program and I know I'm kind of hard to read. So I also give some hints about myself, right? That I say, well, at the top here, you could think of them like kind of like assert statements or something, right? That there's some things about my program that I want you to know. And I either make it easy for you to prove that those things are true about my program, or maybe it's just by reputation, right? So what is a good language if you really imagine AI agents interacting with each other in the wild? What is a good language for them to describe themselves and to make guarantees about themselves, right? In some sense, maybe make promises that are then verified either through reputation or maybe actually by direct analysis of the code, right? And generally, it's easier to prove something about the code if intentionally the code is set up for that, for making it easy to prove that. So I think that's a really interesting direction that I think could have some more near future value as well, right? Like, what is the right way to make statements about agents, code more generally, that will help in making the kind of claims about the program that are useful for cooperation.
Great. Lots of interest. I'm going to make sure to copy the chat because Vince, you have a lot of good questions and comments for you there and links. There will be a Gather Town gathering afterwards. If you look in the chat, you can find the link. So a few people will be there if you want to continue the conversation. Thank you again, everyone, for coming out, and especially Vince for sharing all this exciting research, and Edith and Joe for launching the conversation. So thanks all, and looking forward to seeing you at many future seminars.